Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to be discussing molecular orbital theory. In order to understand molecular orbital theory, we need to take a step back and review the progression of bonding models that has led us here. Chemistry is built on models, each one refining our understanding of how atoms interact to form molecules. The key thing to remember is that no single model fully explains everything. Instead, each theory offers an increasingly accurate approximation that addresses the limitations of the previous model. In this lecture, we're going to trace the development of these bonding theories, and we're going to examine their strengths and weaknesses and how they ultimately point us towards molecular orbital theory. Once we establish why molecular orbital theory is necessary, we're going to learn how to use it, and we're going to learn how to construct molecular orbital diagrams to predict properties like bond order, stability, and magnetism. We're going to begin our understanding of bonding with Lewis structures. This is a simple way to represent how atoms share valence electrons. This model is useful for determining which atoms are connected, the presence of lone pairs, and whether a molecule has resonance structures. But while Lewis structures help us organize electrons, they are limited because they only give us a two-dimensional representation of a molecule. But real molecules exist in three-dimensional space, and this is where VSEPR theory comes in. VSEPR helps predict molecular geometry by assuming that electron pairs repel each other and they're going to arrange themselves in a manner that minimizes those repulsions. This model allows us to determine shapes, and it gives us a better idea of what molecules actually look like. However, while VSEPR tells us where atoms go, it does not explain why bonds form at the atomic level. To explain how atomic orbitals contribute to bonding, we need to talk about valence bond theory. This theory describes bonds as the overlap of atomic orbitals that contain unpaired electrons. It introduces the concept of sigma and pi bonds, and it explains the different types of orbital overlap that occur in single, double, and triple bonds. Valence bond theory also explains hybridization, which allows us to describe bonding in a way that matches experimental molecular geometries. But despite these strengths, valence bond theory still has limitations. It assumes that electrons are always localized within individual bonds. But in reality, some molecules exhibit delocalization, where electrons are actually spread across multiple atoms instead of being confined to one bond. This brings us to molecular orbital theory. Instead of treating bonds as overlapping atomic orbitals between two atoms, molecular orbital theory describes bonding in terms of molecular orbitals that extend over the entire molecule. This model is based on quantum mechanics, and it treats electrons as wave functions that combine constructively or destructively to form bonding and anti-bonding orbitals. The advantage of this approach is that it explains electron delocalization. So, molecular orbital theory gives us a more accurate representation of bonding. But it's also important to note that it is much more mathematically complex. For larger molecules, valence bond theory and hybridization still provide useful approximations. So in practice, both models are used depending on the level of detail required. Now that we've traced the development of bonding models, and we've established why molecular orbital theory is necessary, we're ready to start applying it. The first thing we need to do is to define some key terms and concepts that are going to help us navigate molecular orbital diagrams and understand what they tell us about bonding. This may not make perfect sense right away, but we're going to reinforce this vocabulary throughout the lecture. In molecular orbital theory, when two atomic orbitals combine, they don't just merge into a single new orbital. Instead, they always create two molecular orbitals, one with lower energy and one with higher energy. These two orbitals represent different ways that electrons can exist within a molecule. The lower energy molecular orbital is called a bonding orbital, and the higher energy one is called an anti-bonding orbital. A bonding molecular orbital is going to be stabilizing because it results from the constructive interference between atomic orbitals, meaning the electron density is going to be concentrated between the nuclei. And this increased electron density creates a stronger attraction between the atoms, and that reinforces the bond. Bonding orbitals, they can be either sigma or pi orbitals, depending on the type of overlap between the atomic orbitals. On the other hand, an anti-bonding molecular orbital is destabilizing. It results from destructive interference, meaning the electron density is reduced between the nuclei, and instead a node forms between the atoms. A node is a region of zero electron density. This actually pushes the atoms apart, and it weakens or even prevents bonding. Anti-bonding orbitals are going to be denoted with an asterisk, so we're going to write them either as sigma star or pi star. Now that we know what bonding and anti-bonding orbitals are, we need to introduce a few important vocabulary terms that are going to help us analyze molecular orbital diagrams. First, we have HOMO. This stands for highest occupied molecular orbital. This is the highest energy orbital that actually contains electrons. Then the LUMO, the lowest unoccupied molecular orbital, is going to be the first available orbital that electrons can move into if they were excited. The HOMO and LUMO are particularly important when we discuss chemical reactivity because they define where electrons can be gained or lost in a molecule. For now, just keep these terms in mind. They're going to make more sense when we start drawing molecular orbital diagrams. Another crucial topic in molecular orbital theory is bond order. This tells us how strong a bond is based on the number of bonding and anti-bonding electrons present. A higher bond order means a stronger and shorter bond, while a lower bond order means a weaker and longer bond. If the bond order is 0, this means there are equal numbers of bonding and anti-bonding electrons, so no stable bond forms and the molecule does not exist. Now, when the bond order is equal to 1, this corresponds to a single bond. A bond order of 2 corresponds to a double bond, and a bond order of 3 corresponds to a triple bond. However, in molecular orbital theory, we can also have fractional bond orders like 0.5, 1.5, or 2.5, and this happens when there is partial bonding due to electron delocalization. Finally, we need to distinguish between two important terms, paramagnetic and diamagnetic. This is actually one of the biggest advantages of molecular orbital theory, over valence bond theory because it correctly predicts the magnetic properties of molecules. If a molecule has unpaired electrons, it's paramagnetic, meaning it's attracted to a magnetic field. But if all of the electrons are paired, then the molecule is diamagnetic, meaning it's not attracted to a magnetic field. And this distinction is really important when we analyze molecular orbital diagrams. Now that we've introduced the fundamental concepts of molecular orbital theory, it's time for us to learn how to construct molecular orbital diagrams. Since our focus in this class is mainly on diatomic molecules in periods 1 and 2, we need to start with the most basic case, the overlap of 1s atomic orbitals. This is the foundation for everything else we're going to build in this lecture. To begin, let's consider the simplest molecule, dihydrogen. Hydrogen has just one electron in a 1s orbital, meaning when two hydrogen atoms come together, their 1s orbitals are going to overlap to form a molecular bond. However, unlike in valence bond theory, where we simply say a bond forms, in molecular orbital theory, this overlap creates two new molecular orbitals. One is a bonding molecular orbital, sigma 1s, and this results from constructive interference, meaning that the atomic orbitals add together in phase. This increases electron density between the two nuclei, which stabilizes the molecule. The second orbital that forms is an anti-bonding molecular orbital, sigma star 1s, which results from destructive interference, meaning the atomic orbitals combine out of phase. This creates a node, which is a region of zero electron density between the nuclei, and this actually pushes them apart and stabilizes the molecule. So in short, the bonding orbital pulls the nuclei together, while the anti-bonding orbital opposes that attraction. Now let's take this idea and let's construct the molecular orbital diagram for dihydrogen. Since each hydrogen atom has one electron, the total number of electrons in dihydrogen is 2. Now, a molecular orbital diagram, it's essentially an energy diagram. We start by drawing the 1s atomic orbitals for each hydrogen atom on either side, each one containing one electron. Then we show that these orbitals combine to form two molecular orbitals. The bonding sigma 1s orbital, which is lower in energy, and the anti-bonding sigma star 1s orbital, which is higher in energy. Now we need to figure out how to fill this diagram. Molecular orbitals, they follow the same principles as atomic orbitals when it comes to electron placement. According to the off-bow principle, electrons fill the lowest energy orbital first before filling up any higher energy orbitals. Then, the Pauli exclusion principle tells us that each orbital can only hold a maximum of 2 electrons with opposite spins. Finally, Hund's rule states that if multiple orbitals of the same energy are available, electrons are going to fill them individually before pairing. In this case, for dihydrogen, we only have 2 electrons, so both of them are going to go into the lowest energy molecular orbital. That's going to be our sigma 1s bonding orbital. To confirm now whether dihydrogen is stable, we can calculate its bond order, which tells us how many chemical bonds exist. The formula for bond order is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. The number of bonding electrons we have is 2. The number of anti-bonding electrons we have are 0, and that's all divided by 2. This is equal to 1. So the bond order for dihydrogen is 1. And that means dihydrogen forms a single bond. And this is exactly what we expect from Lewis structures. This confirms that dihydrogen is a stable molecule. Now let's apply the same exact process to diatomic helium. Each helium has 2 electrons in the 1s orbitals. So when they come together, there's a total of 4 electrons to distribute. When we fill the molecular orbital diagram, we're going to place 2 electrons in the sigma 1s bonding orbital, just like we did for dihydrogen. However, we still have 2 more electrons, and these 2 electrons are going to now occupy the higher energy anti-bonding orbital, the sigma star 1s orbital. Since the bonding and the anti-bonding orbitals now contain the same number of electrons, the bond order calculation is going to be 2 minus 2 divided by 2, and that's equal to 0. A bond order of 0 means that there is no net bonding interaction in diatomic helium. That means this molecule doesn't exist in nature. So this equal number of bonding and anti-bonding electrons cancels out any stabilizing effects. So the helium atoms are going to remain separate rather than forming a diatomic molecule. Now we're ready to move into the next step and talk about 2s atomic orbitals. Just like with the 1s orbitals, when the 2s orbitals overlap, they form 2 molecular orbitals. One lower energy bonding orbital, the sigma 2s orbital, and one higher energy anti-bonding orbital, the sigma star 2s orbital. The bonding orbital, of course, results from constructive interference, where the electron density increases between the 2 nuclei, and that stabilizes the molecule. The anti-bonding orbital, on the other hand, results from destructive interference, which creates a node between the nuclei, and it makes this orbital destabilizing. Now let's take that information and let us construct a molecular orbital diagram for dilithium. Since lithium has an electron configuration of 1s2, 2s1, each lithium atom contains both the 1s and 2s atomic orbitals, meaning that each lithium starts with 3 electrons. When we draw the molecular orbital diagram for dilithium, we're going to include both the 1s molecular orbitals and the 2s molecular orbitals to fully represent the system. However, when we're determining bond order, we typically focus only on the valence electrons when we calculate this, which in this case comes from the 2s orbitals only. This is also why some representations of molecular orbital diagrams for dilithium you may find on the internet will only show the 2s molecular orbitals, and they will omit the fully filled non-bonding 1s orbitals. However, for completeness in this lecture, we will account for both. Again, each lithium atom contributes 3 electrons, giving us a total of 6 electrons per dilithium molecule. When the 1s atomic orbitals from both atoms combine, we know they form 2 molecular orbitals. A bonding sigma 1s orbital that's lower in energy, and an anti-bonding sigma star 1s orbital that's higher in energy. Since we have a total of 4 electrons from the 1s orbitals, 2 from each lithium, we're going to place 2 electrons in the sigma 1s bonding orbital And we'll place the other 2 in the sigma star 1s orbital. Because the number of bonding and anti-bonding electrons in the 1s orbital is equal, they cancel out, meaning these orbitals do not contribute to overall bonding. Now let's move on to the 2s orbitals, which are responsible for bonding in valence molecular orbitals. Each lithium contributes just one 2s electron, and that gives us 2 valence electrons to distribute in the 2s molecular orbitals. These orbitals combine to form a bonding sigma 2s orbital that's lower in energy, and an anti-bonding sigma star 2s orbital that's higher in energy. Following the off-bow principle, we fill the lowest energy molecular orbital first. So both of these valence electrons are actually going to go into the sigma 2s bonding orbital. Now we can calculate the bond order, which is going to tell us whether this molecule is stable. For dilithium, we consider only the valence electrons, so only the 2s electrons. Looking over here, we have 2 bonding electrons and 0 anti-bonding electrons. So 2 minus 0 divided by 2 is equal to 1. Since the bond order is equal to 1, that means dilithium forms a stable single bond. And even though here we included the 1s molecular orbitals, we know they do not contribute to bonding because the bonding and anti-bonding interactions here cancel each other out. This confirms that only the 2s valence electrons determine the bond order. And that is why a lot of molecular orbital diagrams sometimes will only draw the molecular orbitals for the valence electrons. But we will always draw the full diagram for completeness. Now let's do the same process for diatomic beryllium. A beryllium atom has an electron configuration of 1s2, 2s2. So when we have 2 beryllium atoms, that means we're going to have a total of 8 electrons to distribute. We'll first look at our 1s orbitals. We place 2 electrons in the sigma 1s bonding orbital, and then we'll place the other 2 electrons in the sigma star 1s anti-bonding orbital. With that, we've accounted for the 4 electrons in the 1s orbitals. Now we can move into the 2s orbitals. Here we have a total of 4 electrons to distribute as well. So we are going to place 2 electrons in the sigma 2s bonding orbital, and then the other 2 electrons in the sigma star 2s anti-bonding orbital. Now let's calculate the bond order. We have in our valence electrons 2 electrons in the bonding orbital and 2 electrons in the anti-bonding orbital. So the bond order here is going to be 2 minus 2 divided by 2, and that's equal to 0. A bond order of 0 tells us that diatomic beryllium does not form a stable bond. So just like we saw with diatomic helium, the equal number of bonding and anti-bonding electrons cancels out any stabilizing effect, meaning diatomic beryllium does not exist as a stable molecule in nature. At this point, we've established a clear pattern. The bond order determines whether a diatomic molecule is stable or not. If the bond order is greater than 0, then the molecule is stable and it will exist. But if it equals 0, then the molecule does not form. With that, we are now ready to introduce the 2p orbitals, which play a major role in bonding for elements in period 2, specifically boron, carbon, nitrogen, oxygen, fluorine, and neon. Unlike s orbitals, which are spherically symmetric, p orbitals have directional shape, meaning the way they interact depends on how they align in space. Because of this, we have to consider 3 different 2p orbitals: 2px, 2py, and 2pz, which are aligned on the x, y, and z axis respectively, and they can combine in different ways to form molecular orbitals. Since molecular orbitals form from the overlap of atomic orbitals, we need to analyze the ways in which p orbitals interact when 2 atoms come together. There are 2 main types of interactions: sigma bonding and pi bonding. And these interactions arise depending on whether the p orbitals overlap head-on or side by side. First, let's consider the 2pz orbitals. These are typically chosen as the reference axis for head-on overlap. When 2pz orbitals approach each other along the internuclear axis, they can undergo constructive interference, forming a sigma 2pz bonding orbital. In this interaction, electron density is concentrated directly between the 2 nuclei, which helps hold the atoms together in a strong bond interaction. However, just as we saw with the s orbitals, there's also an out-of-phase combination where destructive interference creates an anti-bonding molecular orbital that's labeled as sigma star 2pz. This anti-bonding orbital has a node between the nuclei, meaning there's no electron density in that region, and it makes it destabilized. Now let's look at what happens with the other 2p orbitals, 2px and 2py. Unlike 2pz, which aligns along the internuclear axis, these orbitals are aligned or oriented perpendicular to the bond axis, meaning they cannot overlap head-on. Instead, they overlap sideways, leading to the formation of pi molecular orbitals. Let's consider first having 2px orbitals. The in-phase combination is going to result in a pi 2px bonding orbital, where electron density is found right above and right below the plane of the nuclei rather than directly between them. Since this overlap is less direct than sigma bonding, pi bonding tends to be weaker than sigma bonds. Similarly, there's also an out-of-phase combination, which creates an anti-bonding pi star 2px orbital. Here, there are nodes between the atoms that, again, leads to destabilization. We can do the same thing for 2py orbitals. If we have 2py orbitals, they can overlap in phase to form pi 2py bonding orbitals or pi star 2py anti-bonding orbitals. This leads us to an important point. Pi bonding occurs in pairs. Since we have 2p orbitals, 2px and 2py, that overlap in the same way, we actually end up with 2 pi bonding orbitals, one from 2px and one from 2py, and we also end up with 2 pi anti-bonding orbitals, one from 2px and one from 2py. This means that whenever pi bonds form, they always come in sets of 2. So now we can summarize. We've discussed all these combinations of 2p orbitals. What do we get as a total? So when 2 atoms with 2p orbitals approach each other, we actually get 6 new molecular orbitals. 3 of them that are bonding molecular orbitals and 3 of them that are anti-bonding molecular orbitals. The bonding molecular orbitals that we get is a sigma 2p orbital and 2 pi 2p bonding orbitals. What about our anti-bonding molecular orbitals? We get 1 sigma star 2p orbital, and then we get 2 pi star 2p anti-bonding molecular orbitals. The next question we need to answer is, well, what is the order? What is the energy order of these 6 molecular orbitals? Interestingly, when we construct molecular orbital diagrams for period 2 diatomic molecules, we notice that the relative energies of the sigma 2p and the pi 2p orbitals are not always the same across all elements. Specifically in diboron, dicarbon, and dinitrogen, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital. However, for dioxygen, difluorine, and diatomic neon, this order is actually reversed. This variation is caused by an effect known as sp mixing. In smaller atoms like boron, carbon, and nitrogen, the 2s and 2p atomic orbitals are closer in energy, meaning they can interact more strongly. And this mixing shifts the molecular orbital energy levels. Keeping this in mind, we're going to begin by analyzing diboron, dicarbon, and dinitrogen, where the pi 2p bonding orbitals remain lower in energy than the sigma 2p bonding orbital. Let's start with boron. Boron has an atomic number of 5. Its electron configuration is 1s2, 2s2, 2p1. So each boron has a total of 5 electrons. If we have 2 boron atoms, each boron contributing 5 electrons, that gives us a total of 10 electrons to distribute in the molecular orbitals. We're going to start from the lowest energy level. So we begin with the 1s atomic orbitals, which combine to form 2 molecular orbitals, a sigma 1s orbital and a sigma star 1s orbital. Each boron atom contributes 2 electrons in 1s. So we have 4 electrons in total. We'll place 2 in the sigma 1s bonding orbital, and we'll place the other 2 in the sigma star 1s anti-bonding orbital. So we filled up both the bonding and anti-bonding orbitals here in 1s. Next, we move to the 2s atomic orbitals. These form the bonding sigma 2s orbital and the anti-bonding sigma star 2s orbital. Each boron atom contributes 2 electrons in 2s, meaning we have another 4 electrons to place. Following the off-bow principle, we're going to completely fill the sigma 2s orbital with 2 electrons, and then we can fill the sigma star 2s orbital with the other 2 electrons. So now we've completely filled both the bonding and anti-bonding orbitals for 2s. Now we reach the 2p atomic orbitals. This is where things get interesting. Each boron atom contributes 1 electron in its 2p orbital, meaning we now have 2 electrons left to distribute in the 2p molecular orbitals. Based on our earlier discussion for diboron, dicarbon, and dinitrogen, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital due to sp mixing. Since we have to follow Hund's rule, we're going to place one electron in each of the two degenerate pi2p bonding orbitals, both of which remain unpaired. Now that we've distributed all 10 electrons, let's calculate the bond order. When we're calculating the bond order, we consider only the valence electrons because they are the ones participating in bonding interactions. The 1s electrons here are core electrons. They remain localized on the individual atoms, and they do not contribute to molecular bonding in a meaningful way. From our diagram, how many bonding electrons do we have? We have 2 from sigma 2s, and then we have another 2 from pi 2p. So we have a total of 4 bonding electrons. How about anti-bonding electrons? We only have 2. So the bond order is 4 minus 2 divided by 2. This is equal to 1. This means that diboron has a single bond between the 2 boron atoms. In addition, this is the first time we actually encounter unpaired electrons in our drawing of a molecular orbital diagram. This leads us to an important concept: paramagnetic and diamagnetic molecules. A molecule is paramagnetic if it has one or more unpaired electrons, meaning it's attracted to a magnetic field. In contrast, a molecule is diamagnetic if all of its electrons are paired, meaning it's not attracted to a magnetic field, and instead it's slightly repelled. Since diboron has 2 unpaired electrons, this molecule is paramagnetic. Now that we've established the complete MO diagram for diboron, we can go ahead and do the same thing for dicarbon and dinitrogen. For dicarbon, each carbon atom has a total of 6 electrons, and the way it fills the 1s and 2s molecular orbitals is just the same as diboron. What's different is that each carbon atom contributes 2 2p electrons, meaning we now have 4 electrons to place in the 2p molecular orbitals. Just like with diboron, the pi 2p orbitals are lower in energy than the sigma 2p bonding orbital, so we're going to fill them first. Following Hund's rule, we place 1 electron in each of the 2 degenerate pi 2p orbitals before we pair them up. This results in all 4 electrons filling the pi 2p bonding orbitals completely. This means that there are no unpaired electrons in the 2p molecular orbitals, making dicarbon diamagnetic, meaning it only has paired electrons and it's not attracted to the magnetic field. Now let's calculate the bond order. In dicarbon, we're going to have a total of 6 bonding electrons and 2 anti-bonding electrons. So our bond order is 6 minus 2 divided by 2, and that is equal to 2. This means that dicarbon has a double bond, which actually aligns with what we see in the Lewis structure. Now we can move into dinitrogen. The difference here is that dinitrogen, each nitrogen atom actually has 3 electrons in the 2p orbitals. So for dinitrogen, there's a total of 6 electrons to distribute in the 2p molecular orbitals. Just like before, we start by filling the pi 2p bonding orbitals first, placing 1 electron in each before pairing them. That takes care of the first 4 electrons. Then the remaining 2 electrons go into the sigma 2p bonding orbital, which is the next lowest energy level. At this point, All the bonding orbitals in the 2p molecular orbitals are completely filled, and there are no electrons in anti-bonding orbitals. Because all of the electrons are paired, dinitrogen is also diamagnetic, meaning it's not attracted to a magnetic field. Now let's determine the bond order. In dinitrogen, we have a total of 8 bonding electrons and 2 anti-bonding electrons. So our bond order is going to be 8 minus 2 divided by 2. This is equal to 3. This gives dinitrogen a triple bond. With this, we have successfully constructed and analyzed the MO diagrams for diboron, dicarbon, and dinitrogen. Next, we want to move into dioxygen, difluorine, and diatomic neon. Here we'll notice an important change in the ordering of the 2p molecular orbitals. In these molecules specifically, the sigma 2p bonding orbital is now lower in energy than the pi 2p bonding orbitals. Let's start with working through dioxygen. Oxygen has an atomic number of 8, meaning its electron configuration is 1s2, 2s2, 2p4. Since we're constructing an MO diagram for dioxygen, we consider 2 oxygen atoms, each contributing 8 electrons. That gives us a total of 16 electrons to distribute in the molecular orbitals. We're going to start with the lowest energy level, so we begin with the 1s atomic orbitals, which combine to form 2 molecular orbitals, a sigma 1s and a sigma star 1s orbital. Each oxygen atom is going to contribute 2 electrons in 1s, so we have a total of 4 electrons to place. 2 go in the sigma 1s, and the other 2 go in the sigma star 1s orbital. Next, we move to the 2s atomic orbitals, which also form a bonding sigma 2s orbital and an anti-bonding sigma star 2s orbital. Each oxygen atom has 2 electrons in 2s, meaning we have another 4 electrons to place. Following the off-bow principle, we're going to completely fill sigma 2s first, and then we can completely fill sigma star 2s. Now we reach the 2p atomic orbitals, which form 6 molecular orbitals. A sigma 2p bonding orbital, 2 pi 2p bonding orbitals, 2 pi star 2p anti-bonding orbitals, and a sigma star 2p anti-bonding orbital. Each oxygen atom contributes 4 2p electrons. That gives us a total of 8 electrons to distribute among these orbitals. Following the molecular orbital energy ordering for dioxygen, we're going to place our first 2 electrons in the sigma 2p bonding orbital. Then we're going to place a total of 4 in the pi 2p bonding orbitals. Now we have a remaining of 2 electrons that have to occupy the pi star 2p anti-bonding orbitals. We want to follow Hund's rule here, so we place 1 electron in each orbital before pairing. Now we can determine the bond order. Here we only pay attention to the valence electrons. The bond order is going to tell us the strength and stability of the dioxygen bond. Here we have a total of 2, 4, 6, 8 bonding electrons, and we also have a total of 2, 4 anti-bonding electrons. So our bond order is going to be 8 minus 4 divided by 2, and this is equal to 2. This means that dioxygen has a double bond, and this aligns with what we expect from Lewis structure. Now, the presence of these unpaired electrons that we see in the pi star 2p antibonding orbitals gives dioxygen a unique property. It is paramagnetic. That means dioxygen or oxygen gas is attracted to a magnetic field. Now we want to do difluorine. Each fluorine atom has 5 electrons in 2p, giving us a total of 10 electrons to distribute in the 2p molecular orbitals. We're going to distribute the electrons in the following way. 2 electrons are going to fill the sigma 2p bonding orbital. Then we're going to have 4 electrons fill the 2 degenerate pi 2p bonding orbitals. Then the remaining 4 electrons are going to fill the degenerate pi star 2p antibonding orbitals. So this is the distribution of those 10 electrons. From here, we can calculate the bond order. In the valence electrons here, we have a total of 8 bonding electrons and 6 non-antibonding electrons. So our bond order is going to be 8 minus 6 divided by 2. This is equal to 1. The bond order means that difluorine has a single bond. Something else you'll notice here is that all of the electrons are paired, meaning difluorine is diamagnetic. It's not attracted to the magnetic field. Finally, we want to cover diatomic neon. Each neon atom has 6 electrons in 2p, giving us a total of 12 electrons to distribute in the 2p molecular orbitals. So the way that we're going to distribute the electrons is first we're going to have 2 electrons in the sigma 2p bonding orbital. We'll have 4 electrons in the pi 2p bonding orbitals. Then we'll have another 4 electrons in the pi star 2p anti-bonding orbitals. And finally, the last 2 electrons that are left are going to go in the sigma star 2p anti-bonding orbital. From here, we can calculate the bonding order. We have a total of 8 bonding electrons and a total of 8 anti-bonding electrons. 8 minus 8 divided by 2 is equal to 0. A bond order of 0 means that diatomic neon does not form a stable bond, which explains why diatomic neon doesn't exist in nature. Since all electrons are paired here, diatomic neon is diamagnetic as well. So we have now successfully analyzed the molecular orbital diagrams for all period 2 diatomic molecules. As a final point, I want to discuss briefly how to deal with the molecular orbital diagrams for the cationic or anionic versions of the diatomic molecules we've covered. Whenever we're dealing with a cationic or anionic version of the diatomic molecules we've covered, the process for constructing the molecular orbital diagram remains exactly the same. The key adjustment is making sure to account for the gain or loss of electrons when filling the molecular orbitals and calculating the bond order. If an electron is removed to form a cation, we're going to take it from the highest occupied molecular orbital. If an electron is added, forming an anion, it goes into the lowest available molecular orbital. And these changes obviously can affect the bond order, sometimes resulting in fractional values like 1.5 or 2.5, which indicate a weaker or stronger bond compared to the neutral molecule. Additionally, Adding or removing an electron can also impact the magnetic properties. For example, if we removed an electron, just one electron from paired electrons, then the species may become paramagnetic. Or if an unpaired electron is added, it may remain paramagnetic rather than becoming diamagnetic. We're going to see how to approach these kinds of situations by tackling a couple of practice problems in this last page of our lecture. This first problem says, how many electrons are in the sigma bonding orbitals in di-boron? But boron here has a positive charge. It's a cation. It has lost one electron. To solve this problem, we're going to go ahead and sketch out the molecular orbitals that we have to fill, starting from our sigma 1s bonding orbital, following this with the sigma star 1s anti-bonding orbital, so on and so forth. We're going to draw it in this simplified way just so that we can answer this multiple choice problem as efficiently as possible. We know that each boron atom has 5 electrons. So with 2 boron atoms, we have a total of 10 electrons to distribute into molecular orbitals. But here we have a charge, a positive 1 charge. That means we've lost one of those electrons, so we now have only 9 total electrons to distribute. The manner that we want to do this is by first putting 2 electrons in the sigma 1s bonding orbital. Then we'll place another 2 in the sigma star 1s anti-bonding orbital. Then we'll place 2 more in the sigma 2s bonding orbital, and another 2 in the sigma star 2s anti-bonding orbital. This accounts for 8 out of our 9 electrons. We only have 1 more left to place, and we can place it in one of the degenerate pi 2p bonding orbitals. Now we can answer the question of how many electrons are in the sigma bonding orbitals in di-boron cation. So here we have 2 in this sigma bonding orbital for 1s, and we have another 2 in this sigma 2s bonding orbital. That gives us a total of 4 electrons that are in sigma bonding orbitals in this diatomic species. The correct answer here is going to be C. This next question says, which orbital is the lowest unoccupied molecular orbital in dioxygen? Dioxygen here has an extra charge. It's -1 charge, which means it's gained an electron. Here we have the molecular orbitals that we need to fill. Notice it's different from diboron because dioxygen has a difference in its energy for the pi 2p and the sigma 2p bonding orbitals. This is something you want to keep in mind. Remember the difference because it will make an impact on how you answer problems. So here we have the ordering for dioxygen. Dioxygen, every oxygen atom has a total of 8 electrons. So for 2 oxygen atoms, we have a total of 16 electrons to distribute. Since it has a -1 charge, it has an extra electron. This gives us a total of 17. The way that we want to fill our molecular orbitals is we're going to place 2 in the sigma 1s bonding orbital. We'll place 2 in the sigma star 1s anti-bonding orbital. Then we'll place 2 in the sigma 2s bonding orbital and another 2 in the sigma star 2s anti-bonding orbital. Then we move into our 2p molecular orbitals. We can place 2 in the sigma 2p orbitals, and then we can place another 2 in each of these degenerate pi 2p bonding orbitals. So far, we've accounted for 2, 4, 6, 8, 10, 12, 14. We have 3 more electrons to place. We'll place 1 in each of the degenerate pi star 2p anti-bonding orbitals. And then we have one more so we can pair up one of these pi star 2p anti-bonding orbitals. Now we've accounted for all 17 electrons. This question says which orbital is the lowest unoccupied molecular orbital. The lowest unoccupied molecular orbital is going to be our sigma star 2p anti-bonding orbital. So the correct answer here is going to be C. Let's move on to this next problem. What is the bond order of dinitrogen? Here it's an anion. It's gained one extra electron. In dinitrogen, there's a total of 14 electrons that we can distribute in molecular orbitals, 7 from each nitrogen. But here, dinitrogen has a -1 charge, which means it's gained an extra electron. So we have a total of 15 to distribute into the appropriate molecular orbitals from lowest to highest energy. So we start by placing 2 in the sigma 1s and another 2 in the sigma star 1s orbitals. Then we move into sigma 2s and sigma star 2s. Now we've distributed 8 out of our 15 electrons. We can then place 4 electrons in the degenerate pi 2p bonding orbitals. We can also place another 2 in the sigma 2p bonding orbital. We have distributed 14 out of our 15 electrons. That last electron can be placed in one of the degenerate pi star 2p anti-bonding orbitals. From here, we can calculate the bond order by focusing on the valence electrons. From the valence electrons, we have 2, 4, 6, 8 bonding electrons. And then we have 2, 3 anti-bonding electrons. So 8 minus 3 divided by 2. This is 5 divided by 2, which is equal to 2.5. The bond order is going to be 2.5, which is answer choice C. Now, there's an easier way to do this without having to draw the molecular orbital diagram. We're going to get into that trick in this last problem. This last problem says, according to molecular orbital theory, which molecule has the longest bond length? First, we need to recall that bond length is inversely related to bond order. The higher the bond order, the shorter and stronger the bond. One of the easiest ways to quickly determine bond order for diatomic molecules is by recognizing that bond order is directly related to the total number of electrons in the molecule. We can use a simple reference table like this one, which lists the bond order for common diatomic species based on their electron count. To use this trick, simply count the total number of electrons in the molecule and find where it falls in the table. If the number of electrons is exactly one of the listed values, then you can directly read the bond order off of the table. If the number falls between two values, then the bond order will be the average of those two. So let's put this into practice, starting off with dilithium. Each lithium atom has 3 electrons, so dilithium has a total of 6 electrons. When you have 6 electrons, you're going to have a bond order of 1. Then we can do the same thing here with dioxygen. Each oxygen atom has 8 electrons, and there's 2 of them, so that gives us a total of 16 electrons. This dioxygen also has a -1 charge, so it's gained an electron. That gives us a total of 17 electrons. 17 electrons falls right in between 16 and 18. So to figure out the bond order, we just need to take the average of 1 and 2. 2 plus 1 divided by 2 is going to be equal to 1.5. So the bond order here is 1.5. Then we want to do it for dicarbon. Carbon has 6 electrons. 2 carbons are going to have a total of 12 electrons. That means that the bond order here for 12 electrons is going to be 2. Finally, we do dinitrogen. Nitrogen has 7 electrons, so dinitrogen has a total of 14. We find 14 electrons on the table. The bond order is going to be equal to 3. Now we have a bond order of 1, 1.5, 2, and 3. Remember, bond length is inversely related to bond order. The higher the bond order, the shorter and the stronger the bond. The lower the bond order, the longer and weaker the bond. So we're looking for which molecule has the longest bond length. We're looking for the lowest value of bond order. That's going to be for dilithium. So the correct answer here is A. And with that, we've completed this lecture. I hope that it was helpful. Please let me know if you have any comments, questions down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.